But chicks, as I have mentioned to you, we are going to be doing the final section of the Physical Sciences paper 2, which is your chemistry paper. This is the final section. It's always at the end of the paper, and it rounds off your chemistry paper, of course, and it's called the Fertiliser Industry. This section is a little bit more practical, as it also overlaps into other subjects. It can be considered to overlap into a bit of geography as well. In some academic institutions, agriculture is a separate subject as well. So it overlaps and houses a bit more than just one academic subject, academic house. So it's a bit more practical, and let's jump straight into it. We're going to have a look at the chemical industry first. So what does what does chemistry or the chemical industry have to do with fertilizer industry? Okay, just a bit of introduction first. Okay, you don't need to take this down. But South Africa, obviously, we have a population that's about over 50 million people currently. But that number is currently, as we speak, also increasing. So, obviously, fertilizers are used in the maintenance of healthy crops. Okay, because that plays an important role to provide enough food for the nation. Okay, in terms of vegetables and fruits, etc. Fertilizers are used to provide sufficient nutrients to the soil in order to sustain optimum crop yields. Okay, obviously, if we have a country of that amount of population, we need mass production. All right, we need large outputs. So the use of fertilizers does obviously ensure that we get optimum. Okay, in other words, good quality produce out of the ground, so we can supply enough food to major supermarkets all over the country. Kind of basic. So the first aspects that we're going to discuss of fertilizer industry is called nutrients. Okay, nutrients. So a nutrient is a chemical substance. This is a definition of a nutrient now. It is a chemical substance that is used for the metabolism and the physiology of an organism and is absorbed from the environment. Okay, so that's a very broad definition right there, ladies and gentlemen. Okay, because you get more than one type of nutrient. You get essential, you get macro, and then you get micronutrients. Okay, so if you want to know what all of those are, okay, pop a quick research in on Google if you want to, or you can look in your local textbook that you have and it will explain it further. I've never seen them ask this question in an exam, so that's why I didn't break up the definitions there of those 3 types of nutrients. Okay, but you're more than welcome to go and further find out what all of those mean. Although the last 2, macro and micronutrients, are often, you'll hear them being discussed in the nutrition industry, with your health and nutrition industry, especially your gym rats or your bodybuilders will often, when they talk about nutrition in their training, they'll mention stuff such as macronutrients and micronutrients, and they'll say a term such as count your macros or count your micros. So you can obviously have a balanced diet, etc. Leads to greater muscle growth and all that jargon. So we have 3 types of nutrients as broken up into essential, macro, and micro. In plants, for example, macronutrients include carbon, hydrogen, oxygen, nitrogen, phosphorus, and potassium, while micronutrients, for example, for plants would include iron, chlorine, copper, and zinc. So we obviously can also kind of distinguish between macro and micro. Micro meaning very small, macro meaning quite large. Okay, that's just off the top of the heads, just discussing the prefixes macro and micro. To further discuss nutrients, okay, so on the sidebar here, nutrients that plants absorb from the soil, they are called mineral nutrients. Okay, so what happens with mineral nutrients? Obviously, the nutrients would go into the soil, first mix with the water or dissolve in water, so that the plants can absorb the water as well as the minerals. Okay, and then of course non-mineral nutrients, they are not provided by the soil itself, but they are provided from the environment. So those non-mineral nutrients would obviously be things such as your oxygen, okay, which is obviously comes from the air, carbon, which is also extracted from the air, and then hydrogen, which is extracted from water, okay, H2O, right? Break out hydrogen from there. That's examples of non-mineral. Okay, mineral, of course, like I said, that must first dissolve in water, because water is a carrier. Water will carry that mineral to the plant. So the plant absorbs the water with that mineral in, and so in turn the plant would absorb that nutrient or that mineral as well. I've put in a table which I've extracted from the grade 12 Siyavula textbook. I think it's table 14.1. And there's a table of non-mineral nutrients as well as mineral nutrients. Okay, so just to go through the table briefly, I'll start at the bottom with mineral nutrients. Mineral nutrients, we got hydrogen, phosphorus, and potassium. Okay, in a normal fertilizer bag that you would buy from agricultural store, such as your plant store, maybe I think Stodel sells a fertilizer store packs. You'll find an MPK ratio, which is what we're going to discuss in the upcoming slides. Okay, and this is where your exam questions will therefore be pulled from. Okay, so nitrogen, where is the nutrient found? Its source, it's found in the soil. Okay, as well as your phosphate and your potassium, they're all found in the soil. Okay, and obviously you want to know why is the nutrient needed. So why is nitrogen needed? Well, parts of plant proteins and chlorophyll. Okay, so it boosts the plant growth. Phosphorus is needed for synthesis, in other words, for the plant to grow or boost the growth as well from the root. And then potassium, of course, that's your cell building. So chlorophyll, obviously, chlorophyll is almost like plant sap, or almost like the blood of the plant, so to speak. It's green. Okay, and it obviously fights against the plant getting any type of disease or withering away, so it always ensures the life of the plant. Non-mineral, like I've mentioned, carbon, hydrogen, oxygen. Okay, oxygen also found in water as well as air. Hydrogen found in water, of course, and carbon found in air, CO2. Now, carbon is the component of organic molecules, such as carbohydrates, liquids, and proteins. Your hydrogen and your water, that is part of, your hydrogen and your oxygen, that is part of organic compounds. Okay, again, that should remind you of the section organic chemistry. Now we're going to dive straight into fertilizers and discuss fertilizers a little more concentrately. A fertilizer is a chemical compound, number one, that is given to a plant to promote the growth of the plant or crop. Organic fertilizers, they are made of natural products such as manure or compost. Inorganic fertilizers, they refer to industrially produced compounds. Okay, compounds that are produced in factories, they are sort of synthetic, not as natural, but if you use manure, of course, or compost, sorry, a fly flew in my face, or compost, that will act as a natural fertilizer, because of course there is valuable nutrients in manure of animals such as cows, horses, or any other manure of mammals, etc., etc. So what we have here is the MPK ratio, which is found on your fertilizer bag. Okay, this is an example of a bag of fertilizer. Obviously that's what it will look like inside. Looks almost like a bit of compost soil that is found in this type of packaging, of course. And what you would see, as you see in the picture as well as in the text on the left hand side, is that it contains a set of numbers. An example, I've used 8:2:6, and on the fertilizer bag there in the picture, which is also extracted from the Siyavula textbook, we see the number 6:1:5 in brackets 22. Okay, what you must know is that it's called NPK ratio, and that's because it is nitrogen, phosphate, or phosphorus, and potassium. And it's in that exact order. So the 6 would be your nitrogen, the 1 would be your phosphorus, and the 5 would be your potassium, as in the picture is over here. Same if it was this number over here. 8 would be your nitrogen, 2 would be your phosphorus, and 6 would be your potassium. These numbers are called the MPK ratio, okay, because they give the mass ratio, okay, very important, they give the mass ratio of nitrogen to phosphorus to potassium within the fertilizer. Very important there. So let's unpack it just a little more, excuse the pun. P and K, or phosphorus and potassium, okay, that is present in the fertilizer. Okay, we want to know what percentage of total fertilizer is nitrogen, phosphorus, and potassium. Okay, that's a typical type of question that could arise in your exam paper. Okay, so what we have is, you saw in the previous slide, the bracket was 22 for this type of fertilizer, 6:1:5. In brackets 22. The next slide we have 3:1:5 in brackets 38. What is that number? Okay, well, that number says 38% of the total fertilizer is nitrogen, phosphorus, and potassium. That number is a percentage. Okay, if we add up this ratio, we have 5 plus 3 is 8 plus 1 is 9, meaning that 3 out of 9 is nitrogen, 1 out of 9 parts is phosphorus or phosphate, and 5 out of 9 is potassium. So how we would read this entire number is that 38% of the total fertilizer is nitrogen, potassium, and phosphorus, or nitrogen, phosphorus, and potassium. Meaning that in percentage of nitrogen is that 3 in 9 parts of the 38% contains nitrogen. Percentage of phosphorus would be 1 in every 9 parts of the 38% contains phosphorus, and the percentage of potassium would be that 5 in every 9 parts of the 38% contains potassium. That's how that number is read. That's how every other ratio and number shall be read and will be read. Quite basic. Alright, we're going to take a little bit of a worked example here from the Siavula textbook on MPK ratios. Alright, this is quite a nice little example here. Okay, and I'm going to go through step by step the solutions as well before we tackle one of our own. So, worked example 1. We have a question that says calculate the mass of nitrogen, phosphorus, and potassium that is present in 500 grams of industrial fertilizer with an MPK ratio of 5:2:3 in brackets 40. Okay, so the 5 is your nitrogen, the 2 is your phosphorus, 3 is your potassium, and 40% is obviously 40% of the fertilizer is this ratio. Alright, so solution step 1. First, we need to determine the mass of the total nutrients in the fertilizer sample, because we have a sample here of 500 grams. Okay, that wasn't said for fun. So 40% of the sample contains nutrients, therefore 40% of the 500 grams, alright, which is 0.4 times 500, would give us a total of 200 grams, which contains the nutrients. Okay, let's go through that step again. We are presented with a sample of 500 grams, okay, and we have that ratio 5:2:3, brackets 40, which means that 40% of the sample contains the ratio or the nutrients NPK. Therefore, we need to find out the amount or the mass of the total nutrients that's in the fertilizer sample. So we have 500 grams, 40% of 500 grams gives me 200, meaning that 200 grams would obviously contain the nutrients. Now we need to determine the mass of the specific components. In other words, now we can determine the mass of nitrogen, phosphorus, and potassium that's in the mass sample that actually contains them. Okay? So for every 5 units of nitrogen, there are 2 units of phosphorus and 3 units of potassium. That means the total number is obviously 10, right? Because that's the ratio. So 5 out of the 10 units are nitrogen. So that's simple. 5 divided by 10 times 200, 100 grams would be nitrogen. 2 out of the 10 times 200 would give me 40 grams of phosphorus, and 3 divided by 10 times 200 would give me 60 grams of potassium. If you add this number up, it all adds up to 200, meaning that our amounts in grams have been calculated correctly. Okay, and just by doing that, we have answered the question, which was calculate the mass of nitrogen, phosphorus, and potassium that's present in 500 grams of industrial fertilizer. This is example 2. Example 2 says calculate the mole ratio of an industrial fertilizer with the MPK ratio again of 5:2:3. Okay, and they've given us the percentage, which is obviously 40. So we've already completed this step 1 in the previous question. The Seavula textbook was so kind not to recreate it. So this should all be familiar because the previous worked example was the same amounts. So just to recap, we had a 500 gram sample, okay, and now we just we calculated the mass of nitrogen, phosphorus, and fertilizer, and now they asked us to calculate the moles. All right, the mole ratio of the industrial fertilizer with nitrogen, phosphorus, and potassium. Great. So what do we do now? Now we've got the mass in grams of all of them. We need to calculate the number of moles for each element. Okay, each element in the sample fertilizer. We make use of the mole formula, which is N is equal to mass over molar mass. Okay, now the molar mass for nitrogen we find on the periodic table is 14 grams per mole. Okay, and the mass of nitrogen, was 100 grams. So plug that into the mole formula. The number of moles for nitrogen is 100 grams divided by 14 grams per mole. We get 7,14 moles of nitrogen. We do the same formula for phosphorus and potassium, and we do the same formula, and we get answers for phosphorus 1,29 mole, and for potassium we get 1,53 mole. Alright, so now what do? Now we just decide that we are going to determine the mole ratio by plugging them in the same format. N is to P is to K, which means 7,14 is to 1,29 is to 1,53. Okay, that's the unsimplified mole ratio. To get the mole ratio, we need to divide obviously by the smallest number. Okay, by the smallest number. So we divide by the smallest number, it looks like by 1,29, and we get 5,5 is to 1 is to 1,2. Now the ratio must be expressed as a whole number. So in order to get that as a whole number, we need to obviously get rid of the decimal. So how do we get 5,5 to be rid of the decimal there to make it a whole number, which the closest whole number would be 55, okay, and not 6, because you can't just round it up, you need to get it to that nearest whole number. So we multiply the whole ratio by 10 to get it to express it as a whole number. So we get 55 is to 10 is to 12, because if we must divide it by 10, we'll get back to 5,5 is to 1 is to 1,2. Even though we have expressed that ratio, this is just a little bit of maths, even though we've expressed that ratio in terms of whole numbers, 5,5 is to 1 is to 1,2 is exactly the same ratio as 55 is to 10 is to 12. It's the same as that 3 over 6 is the same as 1 over 2. 5 over 10 is the same as 1 over 2. 10 over 20 is the same as 1 over 2. Why? They all lead you back to a half. Okay? So if you get decimals like 5,5 and 1,2, and you have obviously 1, you need to express it as a whole number. Easiest thing to do is multiply it by 10. Easiest thing. So this wraps up the first part of the fertilizer industry, which is calculating the ratios. The next part is just looking at certain processes that fertilizers go or undergo. Okay, there's, just to name one or two, there's Oswald and Haber process, and that also forms part of your question. This is just one aspect of it, but we will cover that in the next session, where we look at the certain processes that happen around fertilizers.